This is your second installment for Chapter 14. Last time we left with talking about units of the rate constant. So now we're going to continue on with the Chapter 14 lecture material. And in this video, we'll cover three main topics: integrated rate laws, half-life, and collision/transition state theories. And that's a slash because they kind of go hand in hand. So integrated rate laws are basically chemists taking nonlinear data and making it linear. So chemists love straight lines to describe data because it makes things very simple. And so what they do is they take zero order, first order, and second order reactions. They take their rate laws, they integrate them in such a way that the resulting plot of that data is a straight line, and it gives us some very useful information, and it's very conveniently sort of packaged. So let's start off with talking about zero order reactions, because those are the simplest, or zeroth order reactions. Okay, and for the most part, we're going to be using very super generic chemical equations to describe things because it makes it very simple. Okay, and generally we're going to be dealing with some reactant A decaying into products. Okay, because we can talk about that same thing in zeroth order, first order, or second order decay, and it doesn't really matter. So if I take this as my chemical equation, I can write a rate law for it, and that will be the rate equals K times A to the 0 power, right? And anything to the 0 power just equals 1, right? So I can also say the rate just equals the rate constant, okay? And the important thing about zeroth order reactions is that they don't depend on concentration. Of the reactants. Okay, doesn't matter how much reactant I have, the rate is just going to be constant. Okay, so if I plot this data on a graph and I say concentration versus time, I get a straight line. Because if nothing depends on the concentration of A, then the rate will just be a constant decay. No problem whatsoever. So the intercept here tells us A at time 0. So if we're at 0 on the x-axis, that means the concentration of A at time 0. Notice we have a negative slope. Okay. So if our rate is concentration versus time, then the slope equals negative K. Okay? So, or I could say negative slope equals K. Okay? The important thing is that whatever the value for the slope, that's your value of K. So if my slope equals negative 5, then K equals 5. Okay, that also equals the rate. Okay, as we saw with our equation up here, the rate equals K. Okay, so zeroth order is very, very simple, right? And so if we integrate our rate law, okay, we get, and I can, if you want to see the math, consult a calculus book. But, and I could show it to you, but it wouldn't be worth our time. But basically, we take some calculus and we integrate our rate law to describe the line. So for zeroth order, the integrated rate law looks like this. A at time t equals negative kt plus A at time 0. Okay, now let's pay attention to sort of the form of this equation. So if I look at this in a certain way, I can describe this as y equals mx plus b, which is the equation of a straight line. So if I come back to my plot, here's my b, my concentration at time 0, t is my x, a at a given time is my y, and k is my slope. Okay? So my integrated rate law allows me to relate concentration to time. Okay, so if I know any of these pieces, I can find any of the others. So if I know the initial concentration and a concentration at a particular time, I also know time and that new concentration, I can solve for k. Or if I know k and time, I can solve for other components. So the integrated rate law is very, very convenient for us. Now, if you're dealing with these types of problems, generally you will be told what is the order of the reaction. Such and such is a first order, 0th order, second order reaction. And then you can apply the appropriate integrated rate law to that situation. Okay? Or you may be given the information necessary to find what the reaction is, 0, first or second order, which is what we covered in the previous video. Okay? So let's take a look at what a first order integrated rate law looks like. So a first order reaction, we had an example of that in our previous video of the decomposition of hydrogen peroxide, right? H2O plus some oxygen, right? So if I write a rate law for this particular reaction, it's going to look like this. So rate equals K times the concentration of our reactant to the first power. And we don't necessarily need to write that 1 as the exponent, that's implied. So I'm going to go ahead and take it out. Okay? So in first order, the rate actually does depend on the concentration of reactant. Okay? With our 0th order, our reactant was to the 0 power, which equals 1. With first order, we're to the first power. So if I increase or decrease my concentration of peroxide in this reaction, it will affect my rate. Okay? And remember what we saw in the previous video when we were talking about rates. If I just plot the concentration of A versus time in a first order reaction, my plot is not going to be a straight line, it'll be a curved line. Okay? But chemists like their straight lines. Okay? So let's see what we can do to a first order reaction in order to get a straight line out of it. So if I take a generic A goes to products, and I'm told that it's first order, I can say the rate equals the negative delta A over delta T, which equals K times the concentration of A to the first power. Right? So the rate law is also related to the rate of disappearance. Okay? So if I integrate that, in order to get a straight line out of it, my equation now becomes the integrated rate law, first order, will be the natural log of A at time t equals negative kt plus the natural log, that should be an n, sorry, of A at time 0. Okay, it has the same components as the 0th order integrated rate law, but instead of just talking about concentration, we're talking about natural log of concentration, right? So we still have y equals mx plus b. Right? So a plot of the integrated rate law will have the natural log of a over time. It'll have also a negative slope, and the intercept is the natural log of the initial concentration, a at time 0. Okay? So you will be expected to identify the order of the reaction based on a plot that looks like this. So if you have natural log versus time and a negative slope, it'll be a first order reaction. If you have just concentration versus time with a negative linear slope, it'll be 0th order. We'll talk about second order here in just a little bit, but I want to talk about something else before that. Actually, let's get to that. So our next topic is half-life. Okay, so talking about how reactants relate to time and rates of reactions, half-life is our next topic. Okay, so half-life, and that should be an E, the time it takes for half of a reactant to be consumed. Right? Pretty straightforward idea. You know, if you start with 1 gram of substance, when you have half a gram of substance, the time it took for that to get to that point is the half-life. Right? So most commonly we'll be talking about half-life for first order reactions. And the equation for that, T1 half, so time to reach half concentration, equals natural log of 2 over K, or 0.693 over K. Okay, this is for first order half-life. All right. Now, in the handwritten lecture notes that are posted on Canvas, there is a description, a mathematical description on how we can go from the integrated rate law for first order to this equation. But again, it's in the interest of time and expediency, I'm not going to go through that math, but if you'd like to see it, it is written out in the handwritten notes posted in modules. So let's take a look at how we can use this, use these equations, right? Because the integrated rate law and the half-life equation can be used in tandem with each other. So let's do an example here. So we'll switch colors here. So for a generic A goes to products, first order, okay, you'll be told first order reaction. So if we have 1.6 grams of A decomposes for 38 minutes. So at that time, .4 grams are left. What is the half-life? Okay, so your first thing that you might want to do is to go straight to the half-life equation. And that would be a reasonable thought. Right? You're told that it's a first order reaction, so you can use the first order half-life equation. One problem, though, is that we don't know what K is. Okay, so we need the value for K. All right, and where we can get it is in the integrated rate law for first order reactions. Okay? Because in our problem, we are given this information, we're given this information, and we're given this information. Right? We're told that we start with 1.6 grams, we're given a time of 38 minutes, and we're given the concentration at that time of 0.4 grams. Okay, so I can use the integrated rate law to solve for K. Right? So remembering how some of the rules of using logarithms, if I subtract one log from the next, then the effect is that I take the natural log of those two values divided. Okay, so if I rearrange my equation here and say natural log of A at time t minus natural log of A at time 0 equals negative kt, then that's the same thing as saying the natural log of A at time t over A at time 0 equals negative kt. Okay, so at this point, I can go ahead and plug in values for these variables. So I have natural log of 0.4 grams, that's A at time t at 38 minutes, divided by 1.6 grams, which is our initial concentration, equals negative K times 38 minutes. Okay. So when I do this math, I should come out with a value of negative 0.03648 inverse minutes. Equals negative K. So K equals 0.03648 inverse minutes. Tracking at the second significant digit. Sig figs still count, everybody. Don't forget those. So now that I have the value of K, now I can come back to my half-life equation. 0.693 divided by the value of K. Okay, so dividing by inverse minutes will give me just regular minutes as a result. So my half-life is 19 minutes. Okay, so this is how we can go about figuring this out. So let's think about sort of the information that we have. So we start with 1.6 grams. Half of that would be 0.8 grams. Okay, and we arrive at that at 19 minutes. Right? At 38 minutes, we should have less than half, which we do. We actually have only a quarter of that material left. Okay, so the answer does make sense. So our next question that we can tackle, so now that we have these wonderful tools, we can ask the question, how much is left at 1 hour? Okay, so now that we know the value of K, we know the initial concentration, we have a time, we have the value of K, so all that we're missing is the concentration at 1 hour. Right, so we're told it's a first order reaction, and our first order integrated rate law allows us to relate time to concentration. Okay, and so we're given K, keeping in mind that K is in minutes, right? So if I keep my time at 1 hour and I try to apply a K with minutes in the units, things are not going to go well. Okay, so I have to make sure that all of my units match. So time units have to match time units. Mass units have to match mass units. All of that stuff. Okay, so 1 hour is 60 minutes. So my natural log of A at time t equals negative 0.03648 inverse minutes times time, 1 hour, 60 minutes, plus the natural log of the initial concentration. All right. So I'll run through that in arithmetic, then I get an answer of natural log of A at time t equals negative 1.719. Okay, I'm not done yet. So the natural log of A at t does not tell me the concentration of A at time t. Okay, so I need to apply some logarithm magic. So in order to get out of the natural log, I say e to the power. So e to the power of 1.719 will give me concentration of A at 60 minutes. Okay, so if you need to consult a math textbook to refresh your memory on how to deal with logarithms, how to get in and out of them, how to multiply and divide them, add and subtract them, all that good business, I suggest you do it. That's actually beyond the scope of this course. I just don't have the time to do that review with you. That's going to be on you guys. All right. So it's assumed that you've been through a full, term of algebra before starting this class. So we're not going to make you do the calculus, but you should be able to do the algebra for these problems. Okay. So far we've been dealing with all of our examples for zero and first order and for half-life, all that good stuff, has all had a stoichiometry of 1, right? Just A goes to products. What if the stoichiometry isn't 1? Okay, so if I write a generic version of that, I say lowercase a as our stoichiometric coefficient decaying to products. Could be 2a, 3a, 4a, what have you. Okay, if I write a rate equation for this, rate equals negative 1 over the coefficient, delta A over delta T, oops, that A doesn't belong there yet. So still looking at a first order scenario here, okay? So if I rearrange this equation, okay, I'm going to take this and move things around a little bit, rearrange, and I can say the rate equals negative delta A over delta T equals AK. Okay, see that wonderful math magic? All right. So if I integrate that, what we end up with, first order, natural log of A at time t, the equation is going to take largely the same form except for one thing right there. That A, the stoichiometric coefficient, can be put into the integrated rate law. And that's the only thing that changes. Okay, so effectively, this was there all the time. But in our previous examples, we just had a stoichiometric coefficient of 1, so it sort of took care of the problem. Okay, so if A is equal to 1, we can just leave it out, right? But if our stoichiometric coefficient is not 1, we need to make sure that it is in our equation. Okay, and the half-life equation is also affected in the same way. So first order half-life will be 0.693 over AK. So here in just a minute, I'm going to write out a full table that shows all of the stuff for all of the versions, and it'll have that A in there, and so you can see the full versions of all the equations. The last thing I want to do before I get there, though, is to talk about our last version of these reactions, which are second order reactions, right? We talked about zero first, now we're going to talk about second, and that's as far as we're going to go. Right? As far as doing calculations, we're not going to expect you to do third, fourth, or beyond order reactions. We're going to stick with zero, first, and second as far as doing calculations with rate laws. Okay. Now you may end up with problems where the exponents on your reactants are larger, and they may be questions that says what is the overall order of this reaction. That may be third, fourth, fifth, whatever the case may be. All I'm saying is that we're not going to have you do integrated rate law work for anything past second order. Okay, so in a second order reaction with a coefficient of 1, A goes to products. We can write a rate for second order. We can label that second order. So a second order reaction, the rate is going to be K A squared. Okay. So if I had A and B in reactants, then it would be A to the first, B to the first, what have you. But for this simple version of A decomposing, rate equals K times A squared. And the integrated rate law is 1 over A at time t equals positive kt plus 1 over A at time 0. Okay, still y equals mx plus b, right? So if I plot this wonderful business, on my x-axis I'll have 1 over the concentration of A versus time. Right? And in this situation, I will have a positive slope. My intercept is still related to the initial concentration. Okay? So 0th order and first order had negative slopes. Second order is the only one of the three that has a positive slope. Second order half-life. The equation is T1/2 equals 1 over K times the initial concentration. Right? So the half-life depends on both K and A. So it's not constant. Okay, the half-life will depend on how much of the initial component you have, initial concentration of the component. All right, so let's take a look at let's put this all together in a nice table for you to look at. Okay, so for something that includes stoichiometry, okay, our rate equals negative 1 over A delta A over delta T. Right? So that particular piece of equation will take the same form regardless of whether we are first order, second order, 0th order. Right? That rate equals 1 over A, negative 1 over A, delta A over delta T. That will be the same. Okay? What will change are the integrated rate laws. So let's do this in green because green is pleasant. All right, so if my reaction order is 0, so if I'm dealing with a 0th order reaction, the rate law is rate equals K, right? Because it's K a to the 0th power, which is just 1. So rate equals K. The integrated rate law for 0th order is A at time t equals negative AKT plus A at time 0. And I'm writing small because I'm going to be trying to fit a lot of information in this table here. Okay. So K from the graph is the negative slope. Units of K for 0th order are just molarity per second. Okay, and I'll make a separate piece of the table just to show the half-lives, okay, because I don't have enough room on my screen. First order, okay, the rate equals K times A. Right? First order reaction. The integrated rate law, natural log of A at time t equals negative AKT plus natural log of A at time 0. Okay. K will also be negative slope from the graph, and our units of K will just be inverse seconds. Okay. For second order, we'll have rate equals K A squared. Our integrated rate law is 1 over A at time t equals positive AKT plus 1 over A0. Okay, remember, second order is the only one that has a positive slope. So K from the graph will equal the slope, and our units will be inverse molarity seconds. So 1 over molarity times seconds. All right, for 0th order, our half-life equation, right, including stoichiometry, will be half times AK. So the concentration divided by 2, taking into account the stoichiometry and the rate constant. Okay. For first order, half-life is 0.693 over AK. Second order, we have 1 over AK times the initial concentration of A. Okay, so hopefully that helps to clear things up for you. Like I said, most of the problems that you'll run into where you have to deal with time and concentration, you'll be told or given the ability to find what the reaction order is. Okay, you'll be told this is a first order reaction, 0th order, second order, and then you can apply the appropriate integrated rate law to the problem. Okay, so our next topic, so we talked about integrated rate laws, we talked about half-lives, so now we're going to get into collision theory, which will be followed by transition state theory. Okay? So the idea behind collision theory is that we need the correct collision and enough energy, enough energy for a reaction to happen. Okay? So we're talking about things smashing into each other and causing reactions to happen, collisions, right? So if I have some sort of generic equation for generating particulate matter, so taking two gases, reacting them together, and we'll get a solid material as one of our products. So if I have gas A plus gas BC reacting to make solid AB plus some gas C. Okay, so that AB solid is particulate matter. It will actually, depending on its composition and size, may actually stay floating in the air. This is a common sort of reaction that happens with air pollution. Okay, so let's take a look at this sort of from a cartoon standpoint. Let's say that we've got some gas A, and gas A is traveling in this direction. And let's say I've got some gas BC, and it's traveling in this direction. Okay? In order to make our solid, I need A to collide with B, right? So that I can get that AB solid, right? And if A is traveling fast enough, and BC is traveling toward it fast enough, we get a reaction. Okay, we have the correct orientation of A going to collide with B, and they're moving fast enough, they have enough kinetic energy, we have a reaction. Okay, so let's look at a different scenario. If I have gas A traveling in this direction fast enough, right, and in this next scenario, I've got gas BC traveling fast enough, it just bounces off, right? Because I don't have the correct orientation of my molecules, right? In order for a reaction to happen, I need A to hit B, not A to hit C, right? Let's look at a third scenario. Gas A moving along this way. And let's say this time I've got this orientation of my molecule. And let's say it's moving this way also fast enough. Do I have a reaction? Maybe. Right? Because it may make contact with B, but it may not have enough kinetic energy with that contact. Maybe it glances off of B and hits C mostly. Or maybe it glances off of C and hits B and maybe has enough energy left over to cause a reaction. It's not certain. Okay? So again, we need the correct orientation. A's got a lot of stamina, by the way. It's always traveling fast enough. And let's say we have B in the correct orientation, but it's traveling slow. Not enough energy. Okay. They might smash into each other in the correct orientation, but if I don't have enough kinetic energy between the two particles, we don't have a reaction. We have to have enough energy to make the collision actually produce something. Okay. So in this situation that where things are not traveling fast enough, we need enough energy to overcome the activation energy. Okay. Activation energy is an energy barrier. Okay? So we call this E sub A. This is activation energy. And it's a barrier. Okay, so it's a minimum amount of energy that needs to be supplied in order to cause a reaction to happen. Okay, so you may be thinking, wait a second, what about endothermic versus exothermic reactions? Energy going in, energy coming out. Well, we'll look at that here in just a minute with some very nice graphs. Okay, but regardless of that, activation energy is always going to be an issue. Okay. So our next topic, and we will tie these two things together here in just a second, is a thing called transition state theory. Okay. And transition state theory involves a hypothetical state. Between reactants and products. Okay? So quite literally what's happening at the exact moment of a collision. Okay? So we say that's a hypothetical thing because we can't stop the reaction at that moment of collision. It has to continue. We can't pause it. We can't push pause on time, right? So it's a hypothetical thing. So let's look at an example of how this might play out. So if I have a reaction of dinitrogen monoxide plus nitrogen monoxide making nitrogen gas plus nitrogen dioxide. Okay, let's look at this in terms of some Lewis drawings. So if I have my dinitrogen monoxide here plus my monoxide, what's going to happen is those two things are going to collide, and if they have the correct orientation, what we get is a momentary complex where that oxygen is momentarily attached to both things. Right? This is our activated complex. Or we can call it a transition state. Okay? And then at that moment of collision, that's our activated complex or transition state, and then it immediately continues on its path and becomes our products. Okay, that oxygen transfers over to the nitrogen, some bonds rearrange themselves, and voila. Okay, so let's take a look at what this looks like graphically, and this will help to explain the concept of activation energy and how it relates to endothermic versus exothermic. Okay. So if I make a plot of the reaction profile, all right, and let's see, so we're going to have on our y-axis we're going to have energy. Let's say it's in kilojoules because units are always important. And on the x-axis I have reaction progress. So at the very beginning, at the zero reaction progress, I just have reactants, and at the far right of the reaction progress, I will have my products. Okay, so looking at how the energy changes and moves in the course of a reaction. What this reaction is going to look like will take this shape. Okay. So on the left, I'll have my reactants. On the right, I'll have my products. Right? At the top of this will be my transition state. Okay? Or my activated complex. Okay? So some of the other things that this graph tells us are the activation energy. So from the initial point to the top of the transition state, that's the activation energy. Okay, and let's say that it has a value of 209 kilojoules. Right? We also know the difference in energy from the transition state to the products. So that has a value of 348 kilojoules. So between reactants and products, the overall energy change is delta H. Delta H of the reaction. In this case, it will be a negative 139 kilojoules. And if delta H is negative, it's an exothermic reaction. Okay, so endothermic and exothermic refer to the overall reaction energy from reactants to products. If our products have less energy than the reactants, then energy had to be released, hence exothermic. But every reaction still has an energy barrier, and that's our activation energy. Now let's take a peek at our last idea, and that's what an endothermic reaction would look like. So I have my energy in kilojoules over here on the y-axis, and we have our progress on our x-axis. Whoops, I started to draw the wrong graph. Okay, again, we have reactants on the left, products on the right. We have our transition state. Still have our activation energy. We still have our overall change. Of delta H. Delta H is positive. Okay, so we have an endothermic reaction. Right, so whether or not a reaction is endothermic or exothermic depends on the starting and ending points of our reaction. But in the middle, we still have our energy barrier, which is the activation energy. Now, what we're showing here, we're focusing on the forward activation energy. Okay, going from reactants to products. Now, if I had something that I could force back the other way, products going to reactants, my activation energy would be over here. Okay, so depends on which direction you're being asked. Forward activation energy, backward activation energy will dictate which part of that curve you focus on. Right? So this is where I'm going to stop this particular video. Hopefully I didn't have any technical difficulties this time like I did last time. And it's also time for me to get to office hours. So enjoy. I will get the last part of chapter 14 done a little bit later today. And we'll get you going.